In another lecture, I explained to you how you are going to use an SDS gel to be able to separate out your aldolase from other proteins of different sizes. In this lecture, I will explain to you exactly how an SDS gel works the way that it does. So we are using acrylamide, and when we have a solution of acrylamide, we have acrylamide and bisacrylamide in our solution, and we're going to be adding temid and ammonium persulfate to that. So temid is catalyzing the reaction by causing the ammonium persulfate to become a free radical, and then that ammonium persulfate starts the polymerization reaction of the acrylamide molecules. So what happens in a polymerization reaction, if you had acrylamide, just only acrylamide in there, you'd be making long acrylamide chains where one hooks to one, hooks to one, hooks to one, etc. So we also, in addition to the acrylamide molecule, have a bisacrylamide molecule. And occasionally, instead of an acrylamide molecule getting hooked into this chain reaction, we have a bisacrylamide molecule that gets put in this reaction, and this serves to hook one chain of acrylamide to another chain of acrylamide. And basically, what you're doing is you're making a specific pore size between the two chains and the two side bisacrylamides hooking the two chains together. So having different amounts of acrylamide to bisacrylamide ratio, or having different percentages of acrylamide, are able to change the pore size of this acrylamide molecule. So basically, when you're doing this, the lower percentage of acrylamide is able to separate higher molecular weight proteins best. A lower percentage has overall much, much higher pores, so that it allows those larger proteins to get through better. A higher percentage of acrylamide has lots of more concentrated acrylamide, so the higher molecular weight proteins have a tougher time getting through that higher percentage of acrylamide, so it's going to separate lower molecular weight proteins best. So you can have a variety of concentrations from 4% to 20% of acrylamide, and depending on what target size of protein you want to separate. In addition to that, you'd have your ratio of acrylamide to bisacrylamide potentially change. When you are doing proteins, you generally use a ratio of 37.5 to 1 or 29 to 1 parts of acrylamide to bisacrylamide, because proteins generally are more spherical in shape. When you are doing DNA, you generally have a standard ratio of 19 parts of acrylamide to 1 part of bisacrylamide to make the pores a particular size, because DNA is fairly linear in its shape, and it's able to get through those pores based on just simply the length of the DNA molecule. So how exactly is this all working? So you're going to have two different gels on here. You're going to have a resolving gel, which is going to be a higher percentage than the stacking gel. The stacking gel has a very, very low percentage of acrylamide in here, basically serving only to hold the proteins in place so that they are exposed to a particular pH in their situation. The resolving gel has the higher percentage of acrylamide that you want to use to separate out the proteins, and it has a higher level pH. So why these two different pHs? And this is called discontinuous gel electrophoresis. Discontinuous because two different percentages of acrylamide and two different pH levels. Well, the key to all of this is the glycine that you are putting in your buffer, in your gel. Glycine is a Zwitter ion. And a Zwitter ion means that you can have positive and negative charges in the same molecule, and as the pH changes, your net charge on the amino acid glycine can change. So at pH 8.5, there's a net negative charge to the glycine, but at pH 6.9, your glycine is uncharged because it has a positive here and a negative here for a net neutral molecule. So when you have your loading buffer that you're loading in your sample wells right here, you have tris chloride. Tris chloride is your buffer, and you're going to have glycine and you're going to have your proteins. Well, at pH 6.9, chloride carries a charge. Chloride is negatively charged. Glycine has no charge. So as your proteins are being drawn towards the positive electrode, because remember, they have SDS on them, so they're all being drawn towards the positive electrode, it's moving through this pH 6.9 layer. So as the proteins move through this, if the proteins are a little slow, they move to the glycine layer, and the glycine cannot carry a charge, but the proteins are carrying a charge because they're negatively charged because of that SDS, but they're not as negatively charged in a charge to mass ratio as the chloride ions are. So if they go slower, they hit the glycine and they're made to speed up. If they hit the chloride, then the chloride says, no, I've got this, you can slow down now. And so what happens is you're loading a whole bunch of protein. Maybe you have a deep well here that you're loading them in, and as they move through the gel, they're stacking. That's why it's called a stacking gel. They're stacking into a thinner and thinner and thinner layer till by the time they reach the end of the stacking gel, they're just a tiny, tiny, very, very thin layer, and then they hit the resolving gel. Well, when they hit the resolving gel, now that glycine has a negative charge. So the chloride has a negative charge, the glycine has a negative charge, and the proteins have a negative charge, but not in terms of the charge to mass ratio, not as much as the chloride or the glycine. So the chloride and the glycine are zipping on ahead, leaving the proteins to bring up the rear. And so now there's nothing like the glycine was pushing them to go faster because it was uncharged. So if a protein was in the glycine layer up here, the glycine was not carrying the current, so the proteins had to hurry up basically to be in that layer. So now there's nothing pushing the proteins, and now they're able to separate out only according to their molecular weight. So this is what you will see on your SDS gel. You will load proteins in a lane. It will go through the stacking gel. It will stack down to a little line. When it enters the resolving gel right here, then you will start to see a whole bunch of bands separate out according to size. You will only see the marker lanes, though, because our marker lanes happen to have particularly colored proteins attached to each of our marker proteins. Our aldolase and our other proteins from the cell do not have any colors attached to them. So even though this is happening in the gel, you're not going to see it. But we specifically use colored markers so that you can see the separation process in the video happening.